Hello, this video is about chapter 2, one-dimensional kinematics. In this chapter, we're going to learn some concepts for one-dimensional motion. And so those concepts are like position, distance, displacement, speed, velocity, and then we will continue with acceleration. And also we will do some examples on how you can solve one-dimensional kinematics problems. Okay, let's start. So let's start with the concepts. So first of all, don't forget that the concepts that we use in physics, they have special meanings. So they may you may use the same concepts in daily life, but the meanings in the physics context would be special. So for example, position. Position is where the object is with respect to the coordinate system. So whenever you talk about position, there is definitely a coordinate system. So you always specify position with respect to the coordinate system. The position can be positive or negative. So let's see which coordinate systems we have here. So for example, for this coordinate system, the bird is, the position of the bird is x equals 3, right? So, but what about this coordinate system? For this coordinate system, the position is at 0. So the bird is at position 0. And if you look at this one, this is, the position is, it's actually, the positive numbers are in this direction and the negative numbers are in this direction. So this is like negative x. So the position of the bird is x equals -1. And let's say if the bird is moving this way to the right, so with respect to the first and the second coordinate system, the bird would be moving in the positive direction. But with respect to the third coordinate system, the bird, if it's moving this way, so it's actually moving towards the negative side. So we would say it's moving in the negative direction. Okay, so the coordinate system is important. So which coordinate system do you have to use? Well, it's up to you. You can choose any coordinate system to work with. It's completely up to you. But once you choose the coordinate system, let's say you choose this coordinate system, this one, the third one, then you have to stick with it throughout the calculation. So in the middle of calculations, you cannot change your coordinate system. Okay, so we're going to see plots like these. This one is for position. The y-axis is the position, and the x-axis or the horizontal axis is the time. So the position versus time graph will depend on the coordinate system chosen. For example, let's say we choose this coordinate system. So initially the object is at 1 meter, okay, with respect to this coordinate system. So this, on the position graph, so at time equals 0, it will start from 1. So if you chose, let's say, a coordinate system where this point was, let's say, if it's 0, if you choose this coordinate system, then your position graph would be, it would start from 0 like this, and it would go like this, right? If you put your coordinate system at any other point, so the starting point on the position axis will be different. So it depends on, so these plots, they depend on the coordinate system that you choose. Okay, so what's happening here? So what happens is the object is at time, when time equals 0, initially it's at 1 meter. So it's here, okay? And this is time equals 0. And then it starts moving in the, let's say, positive or negative. Well, this is positive direction, so it's moving in the positive direction, okay? At time equals 1, it's actually at 3 meters. Let's see, at time equals 1, it's at 3 meters, okay? So this direction is positive direction, so the object is moving in the positive direction. And it moves to 4 meters, okay, at time equals 2. So it's at 4 meters, time equals 2. Okay, what happens at 4 meters? Well, it's, after this point, it's going to go back in the negative direction. So at 2 seconds, here you can see that, it is the position is still, here the position is still positive, okay, because look at the positions, those are positive numbers, okay, but after this point, it's actually going in the negative direction. See, the positions are here, they're positive numbers, but the object is now going in the negative direction. And at some point, it crosses 1 meter and then 0. So it's actually at this point, 0, and then it goes to -1. So this point is -1. So this is how you interpret these position versus time plots. So a lot of time you're going to use plots like these, position versus time, not like these ones. So you have to get used to these ones. Okay. So let's go on with the concept of displacement. So displacement means the change in position. So this delta is the Greek letter delta, uppercase Greek letter delta. It means the difference or change. It means difference or change. Okay, so whenever you see something like delta, let's say A, it means A final minus A initial, whatever that A is. Here, in this case, it's X, its position. So delta X is X final minus X initial. So this is displacement, is the change in position. And it can be positive or negative, right? If this number is large, then this is positive, but if the initial is larger than final, then you will get a negative number for delta X. Here, X final and X initial are the final and initial positions. Okay, let's think about this example. If you drive from your house, so this is your house here, to the grocery store. Okay, the grocery store is here, so you're gonna go this way. Okay, and then back to your friend's house. This is your friend's house here. So you will go back all the way to your friend's house, and this is your final destination. So what is X final? X final is, see, this point is 0. Okay, this is the position, final position, so X final is 0. What was the X initial? X initial was, well, we're using this, the coordinate system that's given, where origin is here, X equals 0, and your house's initial position, it's 2.1 miles. So if you do X final minus X initial, 0 minus 2.1, so the displacement is negative 2.1 miles. So as you notice, displacement, the concept of displacement is not interested in how much you traveled. It's actually interested in only the final position and the initial position. Well, the difference between them. The other concept is, it's something that we use mostly in daily life. It's distance traveled, or we can also say shortly just distance. It is the total length of travel, and it's always positive. Remember, displacement could be positive or negative, but distance traveled is always positive. So let's think about this. If you drive from your house to the grocery store, so you're going to do the same thing again. You're going to start from here, drive to the grocery store, and then go all the way to your friend's house. Okay. Now, what is the distance traveled? Distance traveled is, well, how much do you travel? 4.3 miles. And then another 4.3 miles here. So 4.3 plus 4.3. And then you go another 2.1 miles. So the total is 10.7 miles. This is distance traveled. The amount of gas your car uses is related to distance traveled, not displacement, but the amount of gas your car uses is related to distance traveled. Okay, let's go on with the concepts of speed and velocity. So these two are sometimes used in interchangeably in daily life, but in physics they have specific meanings and they mean different things. So you have to be careful. Speed is what you see on the speedometer. In the car, you look at this speedometer and then you see what your speed is at that moment. And it's always a positive number, right? You never see negative numbers on the speedometer. As for velocity, it is speed plus direction. So it's the speed that you read here, but it also has the direction inside in the definition. So because it has the direction, it can be positive or negative according to the coordinate system. So here we're, in this chapter, we are talking about one-dimensional motion. So in one dimensions, it could be, positive or negative. But when we do in the following chapters, we will do, let's say, two-dimensional. So it could be x and y. So in that case, the velocity would be a vector. So, it could be north, south, west, and east. But for one-dimensional motion, it can be either positive or negative. So of course, if it's, whether it's going to be positive or negative, it also depends on the coordinate system you choose. Let's think about this man. He's running in this direction to the right. Okay, now does he have positive velocity or is it negative? Well, look at the coordinate system chosen. The right direction is positive, the left direction is negative with respect to this coordinate system. So then this person is running in the positive direction. So he has positive velocity. And then here in the second figure, he is walking to the left, and left is again negative with respect to this coordinate system. So he has negative velocity. So again, the positiveness or negativeness, it depends on the coordinate system you choose. And if you flip the coordinate system, these definitions, positive and negative, they will be flipped as well. Now, let's talk about now averages. So the average velocity, the definition is, you remember, velocity can be positive or negative, and also the average velocity can be positive or negative. The displacement, the final minus initial, this thing, delta x, which, if you remember, x final minus x initial. It can be positive or negative, depending on which one is greater than the other one. And divided by the elapsed time, so this basically means total time. You can think of it as t final minus t initial, or total time. And this is the definition of average velocity. So let me give you an example. Let's say you go from x equals 0 to x equals 50 meters, okay? And then you return to x equals, so you run forward this way, and then from 50 to x equals 0, you walk back. Well, we can't talk about one velocity, right? Because here you're running, but in the return path, you are actually walking. So there are two different velocities. So we can say velocity maybe 1, and here velocity 2. But we can talk about the averages, right? So what is the average? So let's say the whole motion takes 10 seconds. Well, I'm going to use the formula. So x final is, well, finally the person is here, x equals 0. So final position is 0. What was the initial position? Well, it started from 0, then initial position is 0, 2. And I'm going to divide it by the time, 10, but it doesn't matter because this is 0 divided by any number is 0. So the average velocity is 0. Okay, now let's move to average speed. Now, average speed is, speed is always positive. So if you take average of different speeds, then you would always, because those are positive numbers, you would always find the average would be also positive. So its definition is distance traveled divided by the total time. Okay, so now let's look at this example. Now the same situation here, but the only difference is now the question is asking not average velocity, but average speed. Well, the average speed is, find the distance traveled. Okay, so the person goes from here to here first. Okay, what is the distance? It's 50. Okay, and then he goes from here back to 0. What is the distance traveled again? 50 meters. So that's another 50 meters. What is the total time elapsed? Well, it's 10 seconds given in the problem. So if you do the division, you will find 10 meters per second. So the average speed is 10 meters per second. Average speed is the answer to this question. Let's say I traveled from city A to city B at various speeds for 2 hours. What is my average speed? So basically, you travel from A to B, and then you have, throughout the, let's say you are driving, throughout the travel, you were driving at different speeds. You are slowing down sometimes, you are speeding up. So, but you can, the question is like, what is the average speed? So you can take the average. If you drive on highways, you have to be careful not to speed, because not to overspeed, because speed ticketing systems at highways infer, they actually do calculations. They don't watch your speed at every point, but they just infer your average speed from distance divided by time, and they issue a ticket, speeding ticket, if your average speed is over the speed limit. So if from A to B, if it's let's say 100 kilometers, okay, and let's say the maximum speed is 100 kilometers per hour, okay, kilometers per hour. So the maximum, so without speeding, you could go this distance in 1 hour, right? If you travel this distance from A to B less than 1 hour, then let's say, so the distance divided by time would be a smaller number. Let's say, so if you, well, it's actually, okay, so it will be actually a larger number, because so the distance is 100 kilometers divided by, let's say, instead of 100, you draw, let's say, 200 kilometers per hour, okay? That means 30 minutes. So this is way less than the expected time for that travel. So the system can actually issue a ticket, because you actually, from the hour, this hour calculation, it can infer your average speed. Okay, what about instantaneous speed? Well, it is the answer to this question. What is my speed right at this moment? Let's say you are driving, and then you are asking, like, what is my speed right at this moment? And for that, you wouldn't do any calculations. You would just look at the speedometer. So that's the difference between average, which you would calculate, and instantaneous, which means right at this moment. You wouldn't calculate, you would just look at the speedometer. Okay, so these were average speed and instantaneous speed, but we can also talk about average velocity and instantaneous velocity. Remember, velocity was not only speed, but speed and direction. Okay, let's do one definition before we move on. So slope on any graph, let's say I have some graph, some curve like this, the black one. So at any point, I can draw a slope. For example, at that point, the slope will be here. So I'm basically drawing tangent lines. So at this point, the tangent line will be like this. Or if I want to, let's say, draw a tangent line here, it will be like this, okay? The slope of a curve is actually the tangent of the angle of the slope. And the tangent means opposite divided by adjacent. If you remember this triangle, so the tangent or the slope, let's say, if the question is what is the slope of this line? Well, it will be opposite divided by adjacent. Okay, so now we're going to use this definition. So now we are using here position versus time graphs, okay? Okay, so when you are on the position versus time graph, what does the slope give you? Well, slope of the tangent line, so these are different tangent lines that are drawn at different points. They are all tangent. Tangent means touching to the curve at only one point. For example, tangent line at this point, it would touch the curve only at one point, only at this point. So slope of the tangent line, it would give you the instantaneous velocity. Okay, so for example, this is position versus time. If you are asking what is the instantaneous velocity at this time, I'm going to call it T1. Well, what you would do is you would draw a slope, draw a tangent line, and then so you would calculate the slope of this tangent line. How do you calculate it? You have to do opposite divided by adjacent. You can draw a triangle like this if you want, or you can draw any triangle, which you would do opposite divided by adjacent. That will give you the slope. So for this one, it's probably, it could be any number, but so let's say it's +5. Here the slope is less, right? Because the opposite divided by adjacent is less. You can think of it this way, maybe the opposite is less. So that's why the slope is less than this one. And what about this one? Well, for the straight line, the opposite is 0. So it's 0 divided by some number is 0. And the slope for these ones, for this one, for example, is negative, right? So the definition is if for these lines, slope is positive, and for lines like this, the slope is negative. So these were the tangent lines. So again, when you use the tangent line, so when you want the instantaneous velocity, you find the slope of the tangent line. How do you find it? You can find it geometrically, as I explained. You can draw some triangle. Doesn't matter which. It could be small, it could be large, and you will calculate this angle, the tangent of this angle. So it's basically opposite divided by adjacent. Or you can, if you know the function of the curve, as let's say it could be something like this, xt equals maybe t squared minus 3 t to the 4th. It could be anything. I'm just giving an example. You can take the derivative of this one, and it would also give you the slope. But in this, so this class is algebra based, not calculus based. So in this class, we're not going to use derivatives. I'm just giving you information here, extra information. Okay. So this was for instantaneous velocity. What about average velocity? For that, what you have to do is not the tangent line, but you have to draw a chord. You have to draw a chord. So let's say if the question is asking what is the average velocity between t final and t initial, it could be, let's say, 5 seconds, and t initial could be 1 second. What you would do is you would draw a chord like this, okay? And then find the slope of it. Now the slope, you can use this triangle if you want. Okay, so the denominator would be t final minus t initial, right? This distance is t final minus t initial. What about the opposite? Well, the opposite would be, let's draw these lines. So this is x final and this is x initial. So you'll be, this distance it's going to be x final minus x initial. And how do you find this, the slope of the chord? You find it geometrically. So you don't use derivatives here or anything else. Okay, so let's summarize on this curve. So we have the position and time plot. So if this is a car for a car, let's say what's happening here. So the car is, first of all, going in, let's say these numbers are increasing and in the positive direction. So the car is going in the positive direction and starts from 0. So the car starts from 0 from here, and then it moves in the positive direction. This is positive direction. And at some point, it actually stops, right? Because the slope here becomes 0. So it's around like 1.5 seconds. It stops. So, and then let's say it goes here, and then here it stops. And this is maybe time is 1.5, and maybe this point is, let's say 27. X equals 27 meters. And what does it do after that point? Well, it goes a little bit to negative, right? So it went this way, stopped here, and it went in the negative direction. So up to maybe, let's say this probably the position for here is 25. So went back to 25 meters. And then it stops again, and then it goes in the positive direction again. So it makes, again, this motion. So it goes that way. Okay, if you want to find, again, instantaneous velocity, let's say at time equals 1 second, so it will be this point. So time equals 1 second is this point. If you want to find the instantaneous velocity, what you would do is draw a tangent line and then calculate the slope. So it turns out for this plot, the velocity is 10 meters per second. But if you want to calculate average velocities, what you have to do is you have to draw chords. Let's say if you want to calculate average velocity between 0 and time equals 2, then you would do this chord and calculate the slope. But if you're interested in, let's say, the average velocity between time equals 0.5 seconds and let's say time equals 1.5 seconds, then you would use this chord and you would calculate the slope of that chord. So the slope of position versus time graph, it gives us velocity. So I have to warn you that we're now talking, so whenever you see X, it means position. It doesn't mean distance traveled. This is important. So on the plots, on the graphs, the X, the vertical axis, it means the position. So the slope, let's say take this green slope here, it gives you average velocity between times t1 and t2, t1 and t2. What about this one, this chord? If you take this one, it would give you average velocity between t2 and t3. Okay, again, if you want average velocities, you basically draw a chord. But if you are interested in the instantaneous velocity at time t3, then you would draw a tangent line and then calculate the slope. So whenever we talk about average, then we need 2 points, right? For example, these 2 points, these 2 points. But when we talk about instantaneous, then that means we are interested in only 1 point. The question is, what is the velocity right exactly at this time, t3? And just to repeat, if you have a slope like this, these are positive slopes. That means positive velocity. When you have slopes like these are for negative velocity because the slope is negative here and here. Okay, let's do this example. So a car goes from x equals 2. It starts with from x equals 2 meters. You can see it here at time. So this is position again, this is time. It starts from 2 meters. And then it goes to x equals negative 0.37 meters. So it goes to this point, which is in terms of position, x equals negative 3.37. And then what happens is it goes again in the forward direction, and at this time, 3.71, it reaches the position 1. Now, there are a couple of questions. Let's start with the first one. The first one asks, what is the instantaneous velocity at time equals 1? Okay, when it says instantaneous, then we have to talk about, we have to take only that time, only one point, and we have to draw a tangent line. So at 1, you have to draw a tangent line like this. So the green one is the tangent line. The only way to draw this, carefully is basically using computer software. Here I use Mathematica. You could use, MATLAB or other software as well. Otherwise, by hand, you don't know if it's going to be like this or is it going to be like this. So it's really hard to do it by hand, but you can use computer. And so you're basically going to calculate the slope of this tangent line. Okay, how do you calculate it? I can take any triangle on it. I can take it here, or I can take a large one here. But the problem is with these ones, I don't know really these numbers here. What is that number here? I don't know. So what I'm going to do is I'm going to take this large triangle, this one, and then I'm going to calculate the slope. It's going to be basically opposite divided by the adjacent. So this whole thing is, so this point is 0, so 2.5. It's negative because the slope for this one is negative. Divided by, what is this whole thing? From time equals 0 to time equals 2, it's actually 2. So I'm going to divide by 2. If you do this division, you will find the instantaneous velocity to be negative 1.25 meter per second. Okay, the next question is, what is the instantaneous speed at time equals 1? So again, what is the speed at this time? Well, to find it, you can basically just calculate the absolute value of instantaneous velocity. Remember, this could be positive, the instantaneous velocity could be positive or negative. But if you take the absolute value, you will always find the positive number. So I'm going to take the absolute value of this number, which will give me positive 1.25 meter per second. Okay, the next question is, now we did the average instantaneous velocity, instantaneous speed. Now the next one is the average velocity between 0 and 3.71 seconds. Now notice that when we talk about average, now we are talking about two different time intervals. For average velocity, I'm going to use this displacement divided by time, elapsed time. So between time equals 0 and time equals 3.71, okay? What is the final position? Well, the final position at final time is 1. So I'm going to do 1 minus. What is the initial position? It was 2. So it's going to be 1 minus 2, okay, divided by, what is the total time? It's from 0 to 3.71. 3.71. And if you do this calculation, you will find the average velocity is negative 0.27 meter per second. Now, lastly, what is the average speed between time equals 0 to time equals 3.71, which is this final point? For this one, we have to do distance traveled. Remember, this was displacement. But here, now we have distance traveled for average speed. So the time is the same. So it's 3.71, the whole time. And what about the distance traveled? Now you have to be careful while calculating this. So it started from 2, right? And it went to 0. So the total distance here is 2 meters. And then it went to negative 0.37. Okay, it came here. So so this distance is 0.37. So this is 2. Okay, and then it goes back to 0. So there's going to be another 0.37. And then from 0, it goes to the final position, which is 1. So you have to add all these numbers and divide it by the time. You will find the average speed is 1 meter per second. Now, I want you guys to notice that these are the only relation is, these numbers are related by an absolute value, but all other numbers, the average speed is different than average velocity, and these two numbers are also different than the instantaneous speed and velocity. Okay, let's move to acceleration. If you remember from the earlier slides, we defined velocity, which could be positive or negative, as the change in position. And it could also be positive or negative. So the formula is velocity is change in position divided by time. So it's change of position in respect to time. Now, the definition of acceleration, on the other hand, again, it could be also positive or negative, is the change in velocity. So velocity is change in position with respect to time, and acceleration is change in velocity with respect to time. And the formula is this. So we are going to discuss the relationship between what happens when the acceleration and velocity are in the same direction, like in A and B, and what happens when they're in opposite directions, like in B and C, in the next slide. But before that, we have to be careful. So whenever you see X on one side, so here on the right side, that means this direction to the right is defined to be positive direction. So whenever we see a vector pointing to the right, that means it's a positive number. So for example, velocity is positive here. And whenever we see a vector pointing to the left, it's a negative number. So the acceleration here will be negative. Let's see them in detail in the next slide. Okay, so remember the positiveness or negativeness of any quantity, it depends on the coordinate system you choose. Like which direction you define to be positive or negative. In this case, right direction is defined to be positive with respect to this coordinate system. See, that's plus x. So with respect to this coordinate system given in the picture, let's think about all 4 cases. So here the car is going in the forward direction, okay? And the acceleration is in the forward direction. That means this is the case for speeding up. Acceleration being in the same direction with the velocity, that means the velocity will continue increasing, which means speeding up. In the second case, in case B, the car is moving in the forward direction because you can see the velocity vector is to the right, so velocity vector is positive, but the acceleration vector is in the negative direction, so they are in opposite direction, and that means slowing down. This person, even though it's going in the positive direction, he's actually pushing on the brakes. He is slowing down while going in the positive direction. Now, what about the case C? Now, this person is going in negative direction with respect to this coordinate system. If this is x, then this direction is negative x. So the person is going in the negative direction, but the acceleration is in the positive direction. That means, again, just like b, slowing down, because the velocity and the acceleration, they are in the opposite directions. So acceleration is positive, velocity is negative, so it's slowing down. So I want you guys to notice one thing here. So the slowing down is not necessarily related to this negative sign here. You know, the acceleration could be positive in the positive direction, but it could, as in C, but it could again mean slowing down. And finally here, both the acceleration and the velocity, they are in the negative direction, but because they are in the same direction, that corresponds to speeding up. If we defined left to be positive direction, so it could be a coordinate system like this, okay, which we could, I mean, you can define that way, that's fine. Then the signs of A and V, acceleration and velocity, would be opposite. Here, we would get opposite signs. For all positives, we would get negatives. For all negatives, we would get positives if we define the coordinate systems like this. So again, the velocity, if the velocity or acceleration or any quantity, whether it's positive or negative, it depends on the coordinate system. That's very important. And here's a caution. Don't think positive acceleration always means speeding up. No, see, we have positive acceleration here. It actually corresponds to slowing down. So speeding up occurs if the velocity and the acceleration are in the same direction. So case A and case D. So here, velocity and acceleration are in the same direction. And also in case D, they are in the same direction. So there is speeding up here. The speed goes up, the speed goes up. And in the car, so there is the accelerator and there's the brake. If you push on the gas pedal, which is the accelerator, then you would speed up. So it's D and A, and it doesn't matter if you're going in the negative direction or positive direction. You know, when you push on the accelerator, you will speed up. And if you push on the brakes, you will slow down or speed down. Now, let's move to average acceleration. It's just like the definition is, just looks like the average velocity, but instead of x divided by t, here we have v divided by t. And because acceleration is a vector, again, it could be positive or negative. Now, in the previous slides, we looked at the slope on the xt graph, the position versus time graph. But here what we have is now velocity versus time graph. This is important. This is velocity because, you know, this could go to negative also. Velocity can be positive or negative. Because it could be negative, this is not speed. This is an important thing that you have to keep in mind. So, and when you look at the slope on the VT graph, it gives you acceleration. So you can look at any point, a particular point like this, and the tangent line, you can look at the slope of the tangent line, and it would give you instantaneous acceleration. But if you choose different times, two different times, and then draw the chord and calculate the slope, then it would give you average acceleration. Okay, in this chapter, this table summarizes the equations that you're going to use while solving one-dimensional kinematics problems. Okay, this is pretty much the whole list of the equations that you're going to use. So what are those variables in these equations? Like there is x0, v0. Well, these are x0 and v0 are initial position and initial velocity. They are constants. They are time independent. So they don't change with time. Let's say you have a building and then you throw something with some initial velocity, v0, and then it falls like this to the ground. So during the motion, the time will change, the velocity will change, but the initial velocity that you throw it, it will not be changing. So these are constants. What about x and v? So there is x here, there is v here. They are position and velocity at time t. So they are functions of time, and by definition, they are time dependent. So you can think of them as x of t or v of t. You can see that as time proceeds, these the x and v, they will change because they are time dependent. A is the acceleration. So you can see A enters in this equation and also here and also here. It is acceleration. And in this class, we will only deal with the situations where A is constant. So we will only deal with the problems where acceleration is constant. In general, acceleration may be time dependent as well. And finally, T is the elapsed time or total time. And whenever you see delta x, again, it means final minus initial. And you can also write it as, x minus x0. x0 means also initial. It is the change in position. So delta x is the change in position. Let's do this example. So let's say this ranger is here, and then the ranger sees a deer, okay, at some distance, which is given to be 20 meters. And then as soon as he sees the deer, he pushes on the brakes, and then what he wants is, he wants to slow down and stop without hitting the deer. So if delta x is 20 meters, and if initial velocity is 10 meters per second, what should be the deceleration? Deceleration means acceleration, but slowing down. So what should be the deceleration of the car so that the deer lives? Well, which equation do you have to use from these? You can use different equations. For example, you can use this one. The final velocity, because it wants to stop here, right? The final velocity will be 0. We know the initial velocity, 10, plus. We don't know the deceleration, which will be a, times t. Okay, do we know t? Well, we don't know t, we don't know a. We have two unknowns. So with one equation, you cannot solve for two unknowns. So what you can do is you can use maybe another equation like this. So it would include for x and x0, so you can put the x0 other side to the left-hand side. So you can write it as x minus x0. Okay, let's erase this from here. And this is delta x, right? So it will be 20 meters. And here I know what this is. This is 10. And here I don't know a, and then there is also unknown t squared t. So I have two equations now, and I can solve these together, right? Two equations, two unknowns. But that's taking too much time. Why don't we use another equation? So what's given? So look at the problem. Delta x is given. V0 is given. And the question is, what is the deceleration? So if you look at this final, the last one, this is the final velocity, which is 0, right? So if I put 0 here, equals, what is the initial? Well, it's given 10. I'm going to do 10 squared plus, now, so 2 times, I don't know, a, that's what the question is asking, and delta x is the final minus initial, so the final, it's given in the problem as 20. Okay, so this is like, so this is 100, put it on the left-hand side as negative, so negative 100, let me do it here, negative 100 equals 40a, okay? And if you calculate a from here, so get rid of these, so a will be negative 2.5 meter per second squared. So this should be the acceleration, minimum acceleration, so that the ranger does not hit the deer. Why is it negative? Because if you look at the coordinate system, this direction is positive. Okay, so the car is going in the positive direction. If you get an acceleration in the same direction, what would happen is this would accelerate. So its velocity would increase, right? That's not what we want. We want this to be slowing down. So if the velocity is in this direction, then the acceleration should be in the opposite direction. And according to this coordinate system, look which direction this acceleration is pointing to. It's pointing to the negative direction. And that's why we got negative number at the end. So right is defined to be positive x direction in the figure above. Because of the slowing down, the acceleration is negative. That is, it's in the negative x direction, which is to the left in this case. So that's the meaning of negative in the final result. The other lesson that we learned here, even though you can solve this problem by using this equation and this equation, so the unknowns here a and t, the unknowns here a and t, so we have to solve these together to find a and t. You can do it, 2 equations, 2 unknown, that's fine. You can solve for them, but that's, that's taking too much time. So instead of using these 2 equations, I can actually use just 1 equation to get to the result really quickly. So you have to guess which equation, while solving problems, which equation would get you to the result the quickest way, okay? And you get that skill by solving a lot of problems. Okay, let's now move to the definition of free fall. Free fall has a specific meaning in physics. It means falling of an object only under the influence of gravity. So if there is a resistance which creates friction force, it's not technically called free fall. So for free fall, for something, to be in free fall, only gravity, the only force that acts on that object should be gravity. If there's any other force like a resistance or someone pushing in, then it's not called free fall. So free fall happens in vacuum. Vacuum means there's no air. So you can get vacuums in vacuum chambers on the Earth or on any planet or satellite without an atmosphere. So just like on the moon, there's no atmosphere, so there's practically vacuum on the moon. In this class, we will ignore the effects of air resistance by default unless it's explicitly mentioned. So if the problem doesn't talk about air resistance, then that means you have to take there is no air resistance. Let me show you this video. This is actually an astronaut on the moon. So what they are doing is actually dropping a hammer and a feather. So if you do this experiment on the Earth, what will happen is the feather, the hammer, you can see that this is the hammer. This is the hammer, and there is a feather here. If you do this experiment on the Earth, of course the hammer goes down faster than the feather. But if you do this on the moon, let's see what's going to happen. And keep in mind, there is no atmosphere, so there's no air on the moon. And he's going to drop them now. There you go. So they fell at the same rate at the same time. The reason for that is because there's no air resistance, so everything falls. So they're all in free fall. The only acting force on them is both on the hammer and on the feather. It's just gravity. There's no air resistance, so they basically fall at the same rate at the same time. So an object falling in air is subject to air resistance, and therefore it's not in free fall. It's not free falling. We could call it free fall, remember, only if gravity is the only force that acts on that object. In the figure below, there's more air resistance acting on the paper because it has a large surface area. If you drop a paper like this and a ball, the ball will actually reach the ground faster than the paper does. But what if you crumble the paper like this, so it becomes almost like a ball. So the surface area of the ball and the paper, they become comparable. And they would pretty much fall at the same rate, and they will reach the ground pretty much at the same time. So even though the ball is heavy, the paper is light, but what matters is not their mass, but the surface area. In fact, you can do this little experiment at home on your own. Okay, free fall doesn't necessarily mean falling downward. It means free of any force except gravity. The moon and man-made satellites in the sky are in free fall since there's no air resistance in the sky, and they are only under the effect of gravity. So if you have the Earth and think about the moon, so this is the Earth and this is the moon. So moon goes around the Earth. So we would say the moon is in free fall because the only force that acts on the moon is basically the gravitational pull because of the Earth. So free fall doesn't necessarily mean falling down. In vacuum, a ball thrown is also in free fall after it leaves your hand. So starting here, the ball goes up and down. We will call the object, the ball, is in free fall, not only here, not only while speeding up, but also while going up. So the whole motion is in free fall. Of course, if there's no air resistance. While you are pushing it, so let's say, so the ball is still in your hand and then you are pushing it, you are basically accelerating it, giving it some initial velocity. So while you are pushing it, it's not in free fall. Why? Because, well, the gravity is acting on it, but your hand is also acting on it. It's pushing it. There is a force because of your hand. So it's not in free fall during this motion, since your hand is applying a force on the object, not only the gravity. And when you think about the ball again, here, this situation, So the ball goes up, the velocity is up here, the velocity becomes 0. Here the velocity is down, but if you think about the whole motion, the only force on the ball is always the gravity itself. So that's why we would call this free fall. Okay, let's move to acceleration due to gravity. So the gravity of Earth is approximately 9.8, and the gravity of the moon is about 1/6 of it, so it's approximately 1.6 meter per second squared. And we will in most of the problems we will deal with the gravity on the Earth. So, and a lot of students ask this question: will I use G with positive or negative sign while solving problems? So they ask, am I going to take it negative 9.8 or am I going to take it positive 9.8? The answer is that it depends on the coordinate system you choose. So let's look at this example. So the formula for the height of an object at time t is this. This is one of the formulas that you could again find in the table from the previous slides. Here it's written in terms of y, but it could be, x. It doesn't matter which variable you use. So this is the height at time t. This is the initial position or initial height. This is the initial velocity, y component. And this is the acceleration, which is y component. Now, if the coordinate system is like this, so that defines the up direction as positive, okay? So because the gravity is in the down direction, so if up is positive, then down is negative. Gravity is in the same, so it's in the down direction, and if you define down direction to be negative, then you are going to use negative 9.8. So this equation here it would take negative 9.8. Okay, what about if you define your coordinate system like this? Here, the definition of positive is down. So positive is down, direction is positive. And again, G is, of course, in the down direction here because G and the positive directions are the same. So in this case, you would use positive 9.8. So if it's going to be negative or positive, it completely depends on the coordinate system. You can use the coordinate system on the left, or you can use the coordinate system on the right. So it's up to you. Okay, let's look at this example now. So we have a free fall here from rest. From rest means the initial speed is 0. So it's just released here. It's not thrown down. If you throw something down, then it would have initial velocity, but here it's just released from rest. So initial velocity is 0. So now we have a coordinate system. That coordinate system defines down direction to be positive, okay? Down is positive. So if you look at the formula for x, so for height here, it's, x is used, the variable x, but you can also use y, doesn't matter. So initial position, let's look at our coordinate system. So the ball's initial position is here, and the coordinate system says this point is 0. So I'm going to use 0 for initial position. What is the initial velocity? It says it's released from rest, so it's 0. Here we have 0. And 1/2, now the question is it going to be positive or negative? Down direction is positive, G is always down. So G is in the positive direction, then you would use positive 9.8. And then we also have the t² here. So the formula becomes x equals positive 4.9 t². So this formula would give us the position at different times. For example, let's make a table like this. So when time equals 0, the position, it will give us 4.9, 0 squared, it will give us 0. When time equals 1, okay, so the position will be 4.9. When time equals 2, if you calculate the position, it will be 19.6. Time equals 2. So, and by using this formula, you can calculate the position at different times. Okay, what about the velocity? For velocity, we are using this formula. So in this problem, the initial velocity is 0. So this is going to be 0. So this is gone. And a is the acceleration. We found it should be a positive number, so 9.8 times t. So from here, we can again make a table. What is velocity at different times? So at 0, the velocity is, you can see that it's 0. At time equals 1, the velocity is 9.8 meter per second, and it goes like this. And you can see here, velocity is at time equals 1, it's 9.81. The difference is here in these numbers, the G is used 9.81, but in my calculations, I used approximately, so I actually rounded it, so I used 9.8. So which number are you going to use? 9.81, 9.8, or even 10? It's usually specified in the problem. If nothing is said, just use 9.8. And at other times, you can also find the velocity. And you can see that the velocity is actually going linear, right? Here it goes from 0 to 9.81, and here it doubles, here it triples. The reason of that linearity is because of that linear t. It's to the power 1. But the position, it's not linear. It goes from 0 to approximately 5. And then so here it falls 5 meters approximately. And here it falls about 15 meters. Here it falls about 25 meters. And the reason of this is because there is t squared here. Now, as an exercise, you can answer this question: how would x and v change if up direction was chosen to be positive instead of choosing down direction as positive? What would happen if you use a coordinate system like this? You can think about this as an exercise. Okay, on the right is shown xt graph, which is this one, velocity time graph. So this is position time, this is velocity time, and also the acceleration versus time graph. For the motion of the ball, right after it was thrown upward. So from this point, from this time to the time that it falls back to the 0. So this is the coordinate system that I'm going to use. So this point is 0. The gravity of Earth in this problem, it's pointing down, right? It's always down. So now if you look at this coordinate system, down is negative. So the gravity of Earth will be negative 9.8 in this problem. And why is it negative? Because I chose this coordinate system. So if it's negative and the gravity of Earth is not changing, it's a constant. And if you look at the acceleration versus time graph, it's always constant and its value is negative 9.8. Let's look at velocity versus time graph. Now, if you throw something up, you throw it with some initial velocity, right? And then at the top, the velocity becomes 0, and it comes back with the same initial velocity, but in the opposite direction. Okay, if you look at here at time equals 0, there is some positive number here, maybe 10, but it's positive. And for this coordinate system, it makes sense. Up direction is positive. This is in the up direction, so the initial velocity is positive. If you use the opposite coordinate system, then the velocity would start from here. And then what's happening? The velocity is throughout this motion up to this zero velocity. It's at some positive number. It's decreasing and becoming 0, but it's still positive. You can see that these numbers are, maybe it's going down to 8 and then 5, but it's always positive numbers. And it makes sense. Again, up direction is positive. And at some point, it stops at the top, which is this point, velocity is 0. Now, what happens after that? It turns down, and down direction is, with respect to this coordinate system, is negative. So the velocity now becomes, let's say, -1, -5, and it goes down to -10. So if you change the coordinate system, the acceleration will be like this, right? It will be positive then. And if you, again, change the coordinate system like this, if you use this, then instead of a slope like this, you would get a slope like this. So the lesson here is these graphs depend on the coordinate system chosen. And finally, let's look at the position graph. So this point is 0, right? This point is 0. So the initial position, if you look at, so it starts from 0, so x0 is 0. So it will start from 0 on the graph. And it will move in the positive direction. So it's moving in the positive direction. And then it comes to some distance. So it comes to, let's say, if this distance is 10 meters, so this point is 10 meters. And after that point, it doesn't go to 11, 12, but it goes back. So it will now, because it's falling down, the maximum is 10 meters, then it would start decreasing like 9, maybe 5 meters, and then 1 meter, and then it goes back to 0 again, which is this point. So this is how you interpret the graphs, or if you are given the motion and the coordinate system, then you can always, draw these graphs with respect to the coordinate system. So what are the possibilities? Well, you can see on this graph for constant acceleration. Remember, in this chapter, we do constant acceleration. These are all the possibilities for position, velocity, and acceleration. If these plots belong to the motion of a car, what does that car is doing in each section of the graph? Now look at here, the acceleration is positive initially. Let's start, so let's say this object or car starts from 0. Let's say this is our coordinate system. So there is some positive acceleration. That means the velocity is increasing. Okay, remember the slope of the velocity graph, it gives you the acceleration. The slope is the same, right? It doesn't change. So it corresponds to constant acceleration. So, and, okay, let's put it here again. Or maybe let's do it this way. This is x equals 0. So initially, it goes from x equals 0 to, let's make up some number, 1 meter. Okay, it's going to go from x equals 0 to x equals 1 while increasing its speed. And then in the second section, the speed is constant. So it's going to move from 1 meter to, let's make up another number, 3 meters. So here it's speeding up, but after this point, it is going with constant speed. Okay, now when you have constant speed, now look at here, look at the slope. slope is this. What is opposite divided by adjacent? Well, the opposite is 0 because this is, you know, flat. So the slope is 0, and slope gives you the acceleration, and you can see that in this section the acceleration is 0. And you can also look at the slope here in the xt graph. Now look at the slope at this point. It's like this. Look at the slope at this point. It's like this. Now the slope is increasing, right? And what does the slope give you? The slope in the xt graph, well, it gives you the velocity. The slope is increasing, the velocity is increasing. Okay, and what about here? Here, the object or the car goes from 3 meters, let's say, to 5 meters. Now it's going to go from here to here. And the motion is, and you can look at here, it's going to stop here and then not move as time passes. The position doesn't change. That means it's going to stop for some time, right? So if this is the point where it stops, then that means the velocity goes to 0 here. Let's see, look at the velocity graph. Yes, indeed, it goes to 0. And then it stays as 0. The velocity stays as 0, because if you stopped here and if you are just, you know, staying here, the velocity should be 0. And again, you can look at the slope. If the velocity is not changing, the acceleration is 0. Again, you can interpret the velocity from here. The slope is 0, so the change in x, the change in position is 0, so the velocity should be 0. So change in, or the slope in the xt graph gives you vt graph, the velocity, and the change in, or the slope in vt graph gives you acceleration. So you can go from x to v or v to a by just looking at the slope or the change. Now, in this section, what happens is it's at 5 meters and then it's going to go to 3 meters. So it will now go this way. So this is, it was stopping here and then it, you know, it starts increasing. The velocity is increasing, but in the negative direction. So the velocity becomes more and more negative. But the position is still at positive numbers, right? Because it's going from 5 to 3. These are positive numbers. That's why we have the position graph above the 0 line. Now, look at the slope here. The slope will be negative, right? And constant. You can draw the slope here, it's like this. You can draw the slope here, it's like this. It is the same slope throughout. So that gives you a constant acceleration, but of course it's negative. And you can interpret the constant negative acceleration from this here as well. So you were stopping here and then you started moving in the negative direction. That means your acceleration here in this direction. And then you can interpret the other ones as well. Okay, this is our final example. So the problem is you have a building like this, and then the height of the building is 100 meters, and you throw some ball in the upward direction with initial velocity. This is v0, 20 meters per second. So this is the physics, right? So the physics is this, and that's the problem. Now, you can solve this problem by choosing different coordinate systems. Like you can choose this one, you can put your coordinate system here, you can put even like, you know, different coordinate systems like these. But I'm going to use this one, and I'm going to solve this problem with respect to this coordinate system. And in the next slide, I will tell you what happens if you choose different coordinate systems and how would the solution change. Okay, let's stick to this coordinate system now. The first question is, at time equals 1, find position. So what is the position y? Now, so let's write, so this is the formula that we're going to use. Again, this is from the table that you saw in the earlier slides. Now, when you plug the numbers in the equation, you always plug the numbers with respect to the coordinate system you choose. So the initial position, let's see what the initial position of the ball is. Well, you may say it's 100 meters, but you know, our coordinate system is not, the 0 is not here. The 0 is actually here. So the ball is initially at 0. So the initial position is actually 0 because we are using this coordinate system. So the initial position is 0. What is the initial velocity? Now look at this. So it's in the up direction and 20. Is up direction positive or negative with respect to this coordinate system? Well, its up direction is positive, down direction is negative. Okay. So its magnitude is 20 and its sign with respect to this coordinate system is positive. So I'm going to use positive 20. And the question says, what is, use time equals 1 second. So for t, use 1. And as for the acceleration, so acceleration, the gravity is always down, and down direction is negative. So that means for g, I'm going to use negative 9.8. And then finally, again, for t, use 1. If you do this calculation, you will find the position of the ball at time equals 1 is 15.1 meters. So first of all, it's a positive number. So you have to start from here and go in the direction 15 meters. So it will be at height 15 meters from this point. So it will be, the ball would be either here or here. And this height will be 15 meters. That's time equals 1. Now in the second part of the problem, it says find position now at time equals 5. So what happens, so where would the ball be after 5 second passes after you throw it up? Again, the initial position is 0. The initial velocity is 20 and it should be positive with respect to this coordinate system. Now instead of 1 here, you just, what you do is just plug 5 and 5 squared for t. And the calculation gives you negative 22.5 meters. So again, remember, this is positive. So 0, positive numbers are above this line, and the negative numbers are below this line. So if this is 100 meters, negative 22.5, so go in the negative direction for 22.5. So it will be approximately, if this is 22.5 meters, maybe somewhere here. So the ball would be somewhere here at t equals 5 seconds. Okay, the third part, what is the, so how much time does it take for the ball to get to the top? So from here to the top, how much time passes? For this one, I am going to use this equation, the equation for the formula for velocity. So now at the top, we know that the velocity becomes 0 because, you know, momentarily it stops at the top. So I'm going to use 0 for that. Initial velocity is again 20. The acceleration is negative 9.8, and t is the thing that, the variable that we're going to solve for. And if you solve for t, you find 2 seconds. So that means it takes 2 seconds for the ball to come from here to go all the way to the top. Now the final part is, what is time? How much time passes until the ball hits the ground? So the ball is thrown from the top of the building, and then it goes up and then hits the ground, how much time passes in total? So for this one, I'm going to use the equation that I used in the first and second part. Now, the final position, y, will be what? So the final position is here. What is the position, this point, with respect to this coordinate system? Well, it's definitely the negative way, right? So if this is 0, this point is 0, and these are negative numbers going down, and this point would be y equals -100. Okay, so that's why I'm going to use -100. Initial position is 0, initial velocity is 20, time, I don't know, that's what I'm going to solve for it. And acceleration is again -9.8, and again, there is another unknown. So if you look at this equation, there's one equation and one unknown, but it's quadratic. And if you want to brush up on your basic math skills, like solving quadratic equations, you can look at Appendix A in the textbook. So you can remember how you can solve it. And the solution is, there are two solutions. It's either -2.9 or it's 7 seconds. Well, time should be always positive, so we just, omit this possibility. So it can be only 7. So that means from here, the initial position, all the way to the down on the ground, it takes 7 seconds. Okay, what would happen if you chose different coordinate systems? First of all, you can choose any coordinate system. I mean, I show you here 4 possibilities, but you can choose even like coordinate system like this, or you can choose somewhere in the middle like this. All are possible. So there are actually infinitely possible coordinate systems. But let's think about these 4. So this one we already did, right? If you choose this coordinate system, so this point becomes 0. So the initial position is 0. The initial velocity is 20. Yes, it's given, but what is the sign? Well, it's in the up direction. The velocity is in the up direction. This coordinate system defines up direction to be positive. So that's why the velocity, initial velocity, is positive. And if you define up direction to be positive, but the gravity is down, because of that, you have to use, for gravity, you have to use -9.8. What about if I use this coordinate system, now the blue one? Well, again, it defines the initial position as 0. So y0 is again 0. So this is the same. But what changed if you compare this one and this one? Now the initial velocity is negative. Why? Because this coordinate system defines down to be positive and up to be negative. The initial velocity with respect to this blue coordinate system is actually in the negative direction. That's why we use -20. As for the gravity of the Earth, G is again always down, and down direction, this coordinate is, it defines down direction to be positive. That's why you use +9.8. Okay, now let's put the coordinate system on the ground. Okay, if the coordinate system is on the ground, now what is initial position? Well, if this point is 0, up is positive, so initial position is, the ball is actually here, right? Initial position of the ball is here. And this distance is 100 meters. So the initial position is +100. Initial velocity is 20, and this coordinate system defines up to be positive. So that's why it's +20. And because up is positive, down is negative, and G is gravity of Earth is down, the gravity becomes -9.8. And finally, if you use this coordinate system, what changes is, now the initial position is, so this point is 0. So but the ball is, so, okay, the ball is somewhere here. This distance is 100. But if you go this direction, up direction, so this is 0, these are actually negative numbers, right? So this point with respect to this coordinate system becomes negative 100. So that's why the initial position is negative 100. Initial velocity is 20, but the sign is negative because down is positive and up is negative. And the gravity of Earth is positive because of this definition. So that's all for this chapter. Thank you for listening.